Okay, hi guys, can you guys hear me?
Yes.
Okay, all right. So, we start today's lecture. Oh, before I start today's lecture, I would like to make a quick announcement about exam 2. So your exam 2 is going to be right after spring break. So March 22nd will be exam 2. Okay. So the exam will only be available um, March 22nd, 1 p.m. to 2:15 p.m. Okay. And if you need to adjust this exam time, please let me know ahead. And of course, lockdown browser will be utilized. And the exam will consist of 30 to 35 multiple choice questions. Okay, multiple choice questions only. Okay, I did a survey on Web Campus regarding the study guide, and a majority of you guys think that study guide is useful. So I will go ahead and make the study guide again. But again, this is my version of study guide. In order to succeed in the exam, succeed in this course, you have to make your own study guide. Okay, you need to paraphrase everything in your own words using my study guide and using the lecture PowerPoint, using the lecture note. You need to make your own version of study guide. Okay, and then another important thing is that you need to solve all these sample exercises. Okay, these sample exercises highlighted in blue, these exercises you need to solve at least 3 times. Okay, and then what I'm going to do for this exam, I'm going to give out extra credit points. I'm going to create a portal on Web Campus so you can submit. Um, Here are 3 things you need to submit. Um, the first thing you need to submit is your version of study guide. Okay, and then the second thing you need to submit is chapter 16 sample exercises. Okay, solved in your own handwriting. Okay, uh, if you solve it twice and 3 times, it doesn't matter. I just need um, I just need to see one sample exercises. Okay, so there are about 12 sample exercises in chapter 16, and there are about 7 sample exercises in chapter 17. Okay, you need to solve once for every question. Okay, and then upload those 3 on Web Campus. You will get 5 points, extra credit points for your exam 2 score. Okay, I will make the detailed announcement on Web Campus soon. But again, you need to upload your version of study guide and then solved sample exercise of chapter 16 sample exercises and chapter 17 sample exercises. Okay, you can upload everything in one PDF file or separate PDF file. It's up to you, but I will make the detailed announcement soon. Does anybody have any question about exam 2? Okay, so I don't think we're gonna be able to finish the entire chapter 17 today. So I think we're probably gonna be finishing up the solubility part. So wherever we stop today, that's going to be end of exam 2 material. Okay, so the rest of the materials in this chapter is not going to be on the exam. Okay. And then because I am not able to finish the entire chapter 17 today, I need to postpone the deadline for chapter 17 homework. It is chapter 17 homework is currently due March 13th, but I will postpone this deadline. Okay, I will postpone this deadline to sometime later. Okay, I will announce the date. So, however, homeworks on Macmillan Achieve is very, very useful to prep for the exam. So, wherever material I cover today, I encourage you guys to finish up to that part of homework on Macmillan Achieve. Okay, don't wait till the end. And just try to complete everything all at once. Those homework, as you've seen in exam one, Macmillan Achieve homework, sample exercises in a lecture note, a lot of the problems that I saw went over in the lecture note, those are going to be what's going to be on the exam. Okay, so that's that. That's the announcement for the exam. If you have any further questions, send me an email. If you want to schedule an office hour, I can hold office hours even over the spring break. So send me an email if you need help. Okay. So we're going to,
Dr. Lee, sorry, I have a quick question.
yeah,
You said that the exam was on Tuesday that we got back or Thursday? The
Tuesday.
25th? Tuesday? Okay,
Yeah.
thank you.
No, March 22nd. Yep.
Thank you.
All right. So last week I've introduced this map to you where how to find pH value of a buffer system that has been strong acid or strong base added to the buffer. Okay. So we're going to solve uh, we're going to try a sample exercise utilizing the map that we have just learned. Okay, I'm going to read the question. A buffer is made by adding 0.3 mole of acetic acid and 0.3 mole of sodium acetate to enough water to make 1 liter of solution. The pH of the buffer is 4.74. A. Calculate the pH of the solution after 5 milliliter of 4 molar sodium hydroxide solution is added. So it looks like you're adding strong base to the buffer, right? And B, for comparison, calculate pH of a solution made by adding 5 ml of 4 molar sodium hydroxide solution to 1 liter of pure water. Okay, so you're going to compare for question B, you're going to compare the pH between two situations. Situation one, you're at when you add this sodium strong base to a buffer solution versus when you add strong base to a pure water. Okay. Let's try question A first. So according to this map, okay, uh, the e uh, we're going to use this map. In this question, it looks like the equal amount of acid and base, equal concentration of acid and base are mixed to create a buffer solution. Okay, you have 0.3 mole of acetic acid mixed with 0.3 mole of sodium acetate. A strong base, sodium hydroxide, is going to add to disturb this buffer solution. Okay, so you're going to use this part of the map, this route of the map. Okay, so since strong base is added to disturb this solution, which component within the buffer will fight against this strong base? A stranger that has been added to the buffer system. The acidic component will um, will try to neutralize this newly added strong base, right? So then let's write an equation where acidic component of the buffer reacting with this newly added strong base sodium hydroxide. Acetic acid reacting with sodium hydroxide, creating water, creating acetate and water. Okay. According to this map, in order to find the pH, we need to calculate new concentration of acetic acid and new concentration of acetate. Okay, the system is disturbed by this strong base. Now, concentration of acetic acid and concentration of acetate has been fluctuated. They have been changed. Okay, so we need to calculate the new value of concentration of acid and acetic acid and acetate in order to after adding the strong base to the buffer in order to find the pH value. Once we have new concentration of acetic acid and acetate, we're going to use the Henderson-Hasselbalch equation to find this new pH value. Okay, so let's find the new. Let's create a table in order to find the new concentrations. Let's draw a table. So before reaction, you have 0.3 mole of acetic acid. You have, okay, they're working with mole, so I'm going to convert this into mole. Mole of sodium hydroxide is going to be uh, so the mole of hydroxide at sodium hydroxide that has been added to the buffer is 0.02. Okay, I need one more significant figure, mole. So then if 0.02 mole is reacting with this much acid, how much acetate are you generating? Okay, the only much uh, the only amount of acetate that you're able to generate is the amount of hydroxide that you have in the system, right? But before that, the initial amount of acetate is already given in the question here. I'm going to write that information down. So change, change, change in mole, change in concentration. So you're using 0.20 mole of sodium hydroxide to convert acetic acid into acetate. So the acetate amount that you can the maximum amount of acetate you can get is only this much. So you're generating this much of acetate. How about acetic acid? This much of sodium hydroxide is reacting with acetic acid. So this much of acetic acid will participate in the reaction. So then after the reaction, after the reaction, after this reaction, how much acetic acid you have left over, how much sodium hydroxide you have left over, how much acetate you have now in the system. You just have to perform a subtraction. Okay, so after reaction, you are going to have 0.280 mole. You are consuming 100% of the strong base that you're adding in the system, so you're not going to have any base left over. As for the acetate, now you have additional acetate in the system. You had this much floating in the system originally, but due to this reaction, now you have slightly extra acetate floating around in the system. Let me explain the sign again. The negative sign indicates consuming, okay? You're depleting this amount of mole of this and this. Positive sign indicates that you're generating these. So now that we have new mole information of the acetic acid and acetate, let's find the concentration of these two. So for acetic acid, concentration is going to be mole divided by volume. You have 0.280 mole, and the total volume in the system now is going to be 1 liter at 5 ml, or 1 liter at 0.005 liter is going to be 1.005 liter. That equals to 0.8786 molar. The new concentration of acetate is the new mole of acetate divided by total volume in the system, which is 0.3184 molar. Now that we have molarity information, now that we have the new concentration of acid and conjugate base, we're going to use the Henderson-Hasselbalch equation to find the pH value. So what was the Henderson-Hasselbalch equation? pH equals to pKa plus log of concentration of conjugate base over concentration of acid, right? So that's basically pKa plus log of concentration of acetate divided by concentration of acetic acid. This portion, we're good. We have the concentration ready to go. How about pKa? What's the pKa for this system? So you can find pKa two ways. You can find this pKa value by looking up the Ka value of weak acid table in chapter 16. Convert the Ka value into pKa. You can do that, or another way you can do is that the pH of the buffer is given, right? So according to this Henderson-Hasselbalch equation, if pH of the buffer system is 4.74, that means pKa is also 4.74, right? Because buffer solution has equal concentration of conjugate base and weak acid. So this portion is going to be 1. Log 1 is 0. So if this portion is 0, then the buffer solution's pKa is basically the pH, which is 4.74 given in the question, right? So those are two ways that you can find the pKa. So now we have pKa information, we have concentration of acid and conjugate base. Let's find the pH of this system. Plug in all these numbers. pKa is 4.74 times log of concentration of acetate is 0.8786 divided by 0.3184. That equals to 4.8. So what does this pH value tell us? This is a resulting pH after adding this strong base into the buffer solution. Okay, the initial buffer solution's pH was 4.74. After adding this strong base, it only fluctuated very tiny little bit. It only fluctuated um, up, and increased the pH value to 4.8. Okay, so now let's compare with the situation where you add sodium hydroxide into um, pure water.
Professor,
Yeah.
do you think you can go back and
Okay.
explain again why the pH and the pKa are the same? I'm still not understanding it.
Oh, okay. So the here the question already gave us the information that the pH of the buffer is 4.74, right?
Yes.
So this information we already know. pH equals 4.74. This information is already given. So what is the concentration of this conjugate base and concentration of acid of the buffer solution? They have equal concentration of acetate and acetic acid, right? So this concentration and this concentration, they're same. Do you agree with that?
Yes.
Yeah. So if they're same, this ratio is 1, right? This ratio is 1 because they're same. Do you agree with that?
Yes.
So if log 1 is 0, so then what you have is pH equals pKa plus 0. So then for a buffer solution, pH equals pKa. So what is pKa? 4.74. Do you get it now?
Yes, thank you.
Uh-huh.
Professor,
Yeah.
about that question as well, how did you get 1.005?
1.005 is the total volume of the system. So you have e the buffer is 1 liter, right?
Correct.
Okay. So let me so buffer is 1 liter. How much sodium hydroxide did you add?
5 milliliters.
5 milliliter. That's 0.005 liter, right?
Correct.
So the total volume is now 1.005 liter. Do you agree with that?
Okay.
Yeah.
Yeah.
Mm-hmm.
Thank you.
Yeah, sorry, I went over too fast.
Um,
So,
sorry,
oh yeah.
Professor.
Uh-huh.
I'm sorry. Is it supposed to be 0.3184 over 0.8786 to solve for the pH?
Oh, my mistake. Sorry.
Oh, okay.
Yeah, thank you. So
Thank you.
concentration of acetate is 0.3184 divided by 0.8786. Yep.
Thank you.
Okay, moving on to question B. Okay, so to determine a pH of a solution made by adding 0.020 mole of sodium hydroxide in 1 liter of water, you're basically dissolving any compound in water, right? Let's try to, this is a soluble salt, so it will completely dissociate in water, right? So let's determine the concentration of hydroxide in this solution. The concentration of hydroxide, because sodium hydroxide will completely dissociate, concentration of hydroxide is basically concentration of sodium hydroxide. Concentration of hydroxide equals to 0.020 mole divided by volume, which is 1 point, you're also adding 5 ml, which is 0.005 liter. 0.005 liter. The total volume is now 0.005 liter plus 1 liter of water. Okay, so this concentration of hydroxide is 0.020 mole. Okay, when you mix this amount of sodium hydroxide and this amount of water, the hydroxide concentration is going to be this much. Now we have concentration of OH. We can calculate the since we have concentration of hydroxide, we can calculate POH, right? The POH is going to be negative log of concentration of OH, which is negative log of 0.020, that is 1.7. Okay, then pH is basically 14 minus POH, which is 14 minus 1.7 equals to 12.30. Okay, so compare two situations. When you add when you add sodium hydroxide into a buffer solution, the resulted pH was 4.8. Do you see here? The resulted pH was 4.8. But when you add sodium hydroxide into pure water, the pH is now fluctuated up, increased up to 12.3. So this exercise successfully shows you that adding small amount of strong base to a buffer solution only fluctuated pH a little bit, while adding 5 ml of 4 molar sodium hydroxide to water changed the pH value dramatically. Okay? So that's what buffer solutions do. They in this way, they maintain constant, stable pH value throughout the solution. Okay. All right, now that we have good understanding of what buffer solution is, let's move on to learn a technique called titration. Titrations are procedures in which one reactant is slowly added into a solution of another reactant. Okay, so let's say if we're dealing with acid-base titration, a known concentration of acid is slowly added to a known concentration of base, or a known concentration of base is slowly added to a known concentration of acid. So the diagram on the right here, this is showing the titration between known concentration of base and then a known concentration of acid. Okay, the known concentration of base is slowly, drop by drop, added into the unknown concentration of acid. During the addition of sodium hydroxide, the pH of the system will continuously, slowly change, and it will be monitored by a pH meter, a device to measure the pH values. Once the amount of acid equals to that of the base amount, an equivalence point will be reached. So firstly, we're going to learn about titration between strong acid with a strong base. Okay, strong acid with a strong base. So the diagram on the right here is a titration of a known concentration of strong acid and known concentration of strong base. A known concentration of strong acid and known concentration of strong base. The pH value when no base was added, 0 milliliter of sodium hydroxide was. So the pH value when no base was added is extremely low, below 2, right? As we know, strong acid has low value, so that this makes sense. You only have strong acid within the system. And as we slowly add the strong base, the pH value gradually increases, and once the amount of acid and base are equivalent to each other, the equivalent point is reached. Since this equivalent point has equal mole of acid and base, this equivalence point has equal mole of acid and base. Since this equivalence point have equal mole of acid and base, the pH is neutral and close to 7. Okay, and as more base is continuously added, the pH will continuously rise, right? As we know, strong base has high pH value. Okay. So that was a titration of this was titration of a known acid with known base. Titration of a known base, strong base. And known strong acid. Are going to be the graph for this titration looks very similar to the one that we observed previously, except for it looks like it's flipped over. When no acid was added, 0 milliliter of acid is added, the initial pH value of unknown concentration base is extremely high, right? And as acid is slowly added, the pH slowly drops and eventually reaches the equivalence point at pH 7. As more acid is continuously added, the pH value will continuously drop as well. Let's try a sample exercise. Calculate pH when A 49.0 milliliter and B 51.0 milliliter of 0.1 molar sodium hydroxide solution have been added to 50 milliliter of 0.1 molar hydrochloric acid solution. Okay, so you are performing a titration of strong acid and strong base. So for question A, let's see how many moles of let's see how many moles of hydrochloric acid we have in the solution before and after the titration. If we know the number of proton after the titration, we should be able to find the pH value, right? So before the titration, the number of mole of proton is mole of proton is basically 0.100 mole per liter times you have 50 ml. Let's convert everything into liter. 0.0500 liter, 0.0490 liter, 0.0510 liter. So mole is molarity times volume. So 0.0500 liter. Liter and liter cancels. You're going to be left with mole. That equals to 5.00 times 10 to the negative 3 mole. How about sodium hydroxide? How many mole of sodium hydroxide do you have? For sodium hydroxide, you have this much. You are adding this much of sodium hydroxide into a system where it contains this amount of hydrochloric acid. Okay? Since, as you can see here, since base amount is slightly smaller than the acid amount, so there will be some portion, some proton left over that have not been neutralized. Let's find out the amount of concentration of the amount of mole of a proton that's left over. Did not participate in the ratio. Mole of proton left over is basically initial mole of proton minus mole of the base. This equals to 0.10 times 10 to the negative 3 mole. So this basically tells us that you had this to start, but then this amount of base was added. So this amount of acid has been reacted, and you are left with this amount of acid in the system. This amount of acid was not neutralized, was not able to be neutralized by, was not able to get neutralized by the sodium hydroxide because you only had this much of sodium hydroxide. So now that we know that this amount of mole of sodium hydrochloric acid or proton is floating around the system, in order to calculate the pH value, we need to convert mole into concentration, molarity, right? Concentration of proton is going to be mole divided by volume. 0.10 times 10 to the negative 3 mole divided by the volume of the system is the volume of the system is 0.049 plus 0.05. So that is 0.099. How many? 1, 2, 3, 4. 0.0990 liter. So that's going to be 1.0 times 10 to the negative 3 molar. Okay, now we have proton concentration. Can we find pH? Pretty easy, right? So the pH is going to be negative log of concentration of the proton, which is negative log of 1.0 times 10 to the negative 3. That equals to 3. That's the pH of the system. So this pH tells us that when you add this amount of 49 milliliter of 0.1 molar sodium hydroxide solution into 50 ml of 0.1 molar hydrochloric acid solution, the pH will fluctuate, the pH will change, the resulting pH is going to be 3. For
Professor,
this, oh, go ahead.
for the liters, would it be okay if we put 0.1?
0.1. Mm, I think that's fine, but it's kind of risky. You want to keep because you are allowed to have 4 significant figures, right? When you
Right.
add yeah. So if you have 4 significant figures, why would you round up and keep the significant figures? It's going to be less accurate, right? Does that
Yeah,
make
I think
sense?
I'm confused.
Yeah.
Are we adding all 3 of those?
No, we're talking about question A. So you're adding this amount of base into this amount of acid. So the resulting volume is
Oh,
0.0490 plus 0.0500.
right. I was adding the wrong ones.
Yeah, I just
Okay.
converted this ahead of time. Yeah.
Okay.
So yeah, so you're doing addition, right? And you are
Right.
allowed to have 4 significant figures. So I mean, why not keep the 0.990 for more higher accuracy? You know what I mean?
Yeah, it makes
Yeah.
sense. It was my mistake. Sorry. Thank you.
Uh-huh.
You mean
All right, so
3 significant figures?
3. Yeah, sorry, 3. 1, 2, 3. Yep. And we're moving on to question B. In question B, very, very similar, but now you have different volume of the sodium hydroxide adding into hydrochloric acid solution. Okay, so instead of 49 ml, you now have 51 ml of 0.1 molar sodium hydroxide solution adding into hydrochloric solution. So let's try to find pH for that system. We already know how many moles of proton we have before the titration, right? The mole of proton before the titration is this. Copy. Paste. So mole of proton before the titration is this. So before titration, you have this amount of hydrochloric acid floating around in the system. You are adding 51 milliliter. Just keep the significant figure. 51.0 milliliter of sodium hydroxide. 4 molar. Oh, not 4 molar. 0.100 molar sodium hydroxide. So how many mole of sodium hydroxide are you adding? Mole of sodium hydroxide is 0.100 mole per liter times 0.0510 liter equals to 5.1 times 10 to the negative 3 mole. So you're basically adding this this amount of base into this acid. So what can you tell from these values? You have slightly higher mole of base compared to the acid. So now we know for sure that all of the acid will be neutralized by the base, and now the system has a little bit extra of the hydroxide floating around because you have a little bit excess of the sodium hydroxide, right? So let's find the amount of hydroxide that's been left over after finish neutralizing the acid. It's going to be leftover after neutralization reaction. Is going to be 5.1 times 10 to the negative 3 mole minus 5.00 times 10 to the negative 3 mole. That equals to 0.10 times 10 to the negative 3 mole. So this amount of hydroxide is now left over and floating around in the system. We have concentration of hydroxide. We can calculate POH. Use POH to find pH, and that when we're done. So the POH is going to be, oh, before, Oh, sorry. This is not concentration. This is mole of hydroxide left over. So now we need the concentration of hydroxide left over. Concentration is going to be mole divided by volume. The new volume is 0.0500 of hydrochloric acid, adding 0.0510 liter of sodium hydroxide, adding together. So the total volume is equal to 0.1010 liter. So if you divide it by total volume, you have 1.0 times 10 to the negative 3 molar. Now you have concentration of hydroxide. Let's find POH, which is negative log of 1.0 times 10 to the negative 3. That equals to 3. pH is basically 14.0 minus POH equals to 14.0 minus 3 equals to 1100. That's the new pH of the system after adding this amount of sodium hydroxide into the acid. Okay. Let me know if I have to go back. So we have looked at titration between strong acid and strong base. Now we will take a look at titration of weak acid and strong base. Weak acid and strong base. As you can see from the diagram on the right here, this is a titration between a known concentration of weak acid. A known concentration of weak acid. And you have known concentration of strong base adding into the weak acid. The weak acid is acetic acid and the strong base they used is sodium hydroxide. The curve seems to be similar to the titration curve for the strong acid, strong base, but it is slightly different. Okay, since we're starting with weak acid, the starting point has slightly higher pH value and no base is added. And over the course of the addition of strong base, the pH value slowly increase and reach an equivalence point. And note that this equivalence point is no longer 7, it is higher than 7. And I will explain to you why in a little bit. Then continuous addition of strong base will show continuous rise in the pH value. So I will discuss a little bit in detail regarding how to find pH value in this type of titration. How to find pH value. While the titration between strong acid and strong base seemed pretty straightforward and simple, titration of weak acid and strong base is slightly a bit more complicated. So in order to find the initial pH of the weak acid, we can use Ka value to calculate the pH. Slide 30, 30, oops, 35, no, 36, 37 in chapter 16. I went over detail how you can find Ka, how you can use Ka to find pH, okay, for weak acid. So that you can go back and review this. So anyways, we use a Ka value to calculate the pH value for the initial pH of the weak acid, the initial pH of the weak acid. Then at the buffer region, this is called the buffer region. Okay, the buffer region, a region between the initial point and slightly before the equivalence point, this buffer region, this is how you can find the pH value. What happens during this buffer region is that acid and its conjugate base both occur at the same time, just as in buffer solution. For example, let's say you're considering equation between let's say you're considering a titration of this uh, weak acid and strong base. Just before the complete reaction between acetic acid and sodium hydroxide, there will be acetate and acetic acid exist at the same time, just as in buffer solution. Okay, so then we can find the pH of this buffer region using the Henderson-Hasselbalch equation. Okay, and then at equivalence point, so that's the buffer region, use Henderson-Hasselbalch, and at the equivalence point, as I mentioned before, the pH value is higher than 7. Why? This is because at equivalence point, there will be equal mole of this weak acid reacting with strong base, equal mole. So now acetic acid has now completely reacted and transformed into acetate. So now you don't have any more acetic acid at this equivalent point anymore. You only have acetate. However, this acetate is a conjugate base of weak acid, which can react with water to produce hydroxide, right? This can react with water and produce hydroxide, increase the hydroxide concentration. Therefore, due to this side reaction, the pH value is slightly higher than 7, resulting from the basic product of acetate and water reaction. Okay? So again, at equivalence point, you have equal mole of these reacting, so complete reaction. So you don't have any acetic acid in the system anymore at equivalence point. Before you reach equivalence point, this buffer region, you still have acetic acid. Okay, you have less of the base concentration compared to the acetic acid concentration. So now what do you have? You have both this and this in the buffer region. This buffer region. Okay, then it looks just like buffer solution, right? You have both weak acid and conjugate base of the weak acid. So then you can use the Henderson-Hasselbalch equation to find the pH value for that region. And then after the equivalence point, pretty straightforward, the sodium hydroxide concentration will dictate the pH value of the system. Okay. After equivalence point, the continuous addition of sodium hydroxide will dictate the pH value. pH value will continuously rise. So here's a map regarding how to solve problems about pH of weak acid titration. So as you can see from the map, when you add strong base to the solution of weak acid, the weak acid concentration will decrease. And conjugate base concentration will increase due to the reaction. Then, of course, due to the change in concentration of weak acid and conjugate base, the pH value of the system will change as well. Again, this is depicting the situation before reaching an equivalence point. At equivalence point, complete weak acid is going to react with base. Okay, so this is the situation before the reaching the equivalence point. Now, in order to find the new pH, we know that this system contains both weak acid and weak acid and its conjugate base, which is a buffer solution. We use the Henderson-Hasselbalch equation to Henderson-Hasselbalch equation to find the pH value of the system. Okay, right before it reaches equivalence point. Okay, let's try a sample exercise. Calculate the pH of the solution formed when 45 milliliter of 0.1 molar sodium hydroxide is added to 50 milliliter of 0.1 molar acetic acid. Okay, titration between strong base and weak acid, right? The question wants us to find the pH of the solution. Let's write the reaction equation first. Okay, you have acetic acid, weak acid, reacting with strong base, hydroxide, generating acetate and water. Firstly, let's find out how many moles of weak acid and how many moles of strong base we have. So in order to calculate that, we're going to have to convert uh, the molarity into mole. Okay. 45 ml is 0.0450 liter. 50 ml is 0.0500 liter. So the mole is going to be 0.100. Okay, let me. So mole of acetic acid, you have to start is going to be 0.100 mole per liter times 0.0500, which equals to 5.0010 to the negative 3 mole. Mole of sodium hydroxide you're adding into acetic acid is 0.0100 mole times 0.0450 liter equals to 4.50 times 10 to the negative 3 mole. Okay, so all right, we have base mole and the weak acid mole information. Since base concentration is smaller than weak acid concentration, we know that there is some acetic acid left over in the system floating around. We know that some of the acetic acid in the system is floating around. So then we have a system where we have both acid and conjugate base, acetic acid and acetate. We know that we can use Henderson-Hasselbalch equation to find the pH of this system because we know that we have both acid and conjugate base exist within the system. Okay, so after reaction between 5 times 10 to the negative 3 mole of acetic acid and 4.5 10 to the negative 3 mole of sodium hydroxide, how many moles of acetic acid is left over? Let's draw a table to organize this information. Okay, so again, before reaction, you have 5.00 times 10 to the negative 3 mole of acetic acid to start. You have 4.50 times 10 to the negative 3 mole of sodium hydroxide to start. In the beginning, you don't have any acetate. So then how many mole of base has been consumed? You have less mole of base compared to the acetic acid, so you know that all of the base has been consumed. Okay? And then since this much of base was consumed, that means this much of the acid participated in the reaction. And how much acetate did you generate? Since this much of acid and base reacted with each other, this is the maximum amount of acetate you can get out of reacting with this amount of base. So again, the negative sign indicates depletion of these reactants. Positive sign indicates generation of the product. So after reaction, after reaction, how much acetic acid do you have left? You take this minus this apply the change. You have 0.50 times 10 to negative 3 mole left over. If you do this, you don't have any sodium hydroxide anymore. All of the sodium hydroxide has participated in the reaction. As for the acetate, you now have generated 4.50 times 10 to the negative 3 mole of acetic acid. I'm out of space, so I'm just going to go to the next slide. So now that we have mole information, see, we have mole information here. We have mole information of new concentration of acetic acid and new concentration of acetate within the system. We have mole information. Let's convert this into concentration in order to plug into Henderson-Hasselbalch equation. So in order to calculate mole, we need to find the volume. The total volume of the system is, the total volume will be this plus this, right? So the total volume is 0.0500 liter plus 0.0450 liter equals to 0.0950 liter. So then in order to calculate the concentration of acetic acid after the titration within the buffer region is going to be mole of the acetic acid, which is 0.50 times 10 to the negative 3 mole divided by volume 0.0950 liter equals to 0.0053 molar. For the acetate, you have 4.50 times 10 to the negative 3 mole divided by total volume. You have 0.0474 molar of the acetate. So in order to find pH of the system, well, that was the question was asking, you're going to use Henderson-Hasselbalch equation. So the Ka of acetic acid is 1.8 times 10 to negative 5. The acid dissociation constant of weak acid is again provided in the table 16.2 in chapter 16. Okay, so the pKa is going to be, Ka value is given in that table. The pKa is going to be negative log of 1.8 times 10 to the negative 5. That equals to 4.74. Okay, so now let's plug in all the information we have. pKa is 4.74 plus log of concentration of acetate is 0.0474 divided by concentration of acetic acid is 0.0053. That equals to pH value of 5.70. Okay, so
Can we
this
go
is
back really quick, Professor, please?
oh yeah.
Okay, thank you.
Okay, so this is what I have already explained in the previous slide. The ways that weak acid titration differs from strong acid titration. You can look over this on your own because I'm running out of time. I'm going to move on to the indicators. So in order to experimentally determine the pH value of the titration, I mentioned earlier that we can use a pH meter, right? A device. You can stick this device into a solution and monitor the change in the pH value. But you can also use something called indicators, okay? Indicators are basically natural dyes. Okay, so cross this out. I don't want to confuse you. So cross this out. So cross out this first sentence. So it's just know that indicators are natural dyes. Okay, so they change color in response to pH level change. Each indicator will have its own pH range over which it changes color. So indicator is sometimes used to find the equivalence point in titration. Um, you'll have a better idea looking at this diagram. So for an example here, the top graph is titration between strong base, as you can see, you're starting off with high pH value, right? This is titration of strong base and strong acid. To perform this titration, you use indicator to determine the equivalence point. The here we use indicators to determine the equivalence point. So in order to use indicator to determine the equivalence point, what we do is we add in a beaker, okay, we add strong base and we add the dye, okay, and then we use a burette to slowly add the acid, okay, so you have a dye and base mixed together in the beaker. So for this type of titration, you have two choices of dyes that you can use. You can either use dye called phenolphthalein or methyl red. So for the dye called phenolphthalein, this dye only changes color between pH value of 8.3 and pH value of 10. So over the course of titration, when the base amount has reached near the equivalence point, and when the system has pH level around 8.310, this dye turns from clear color to purple color. So when you see solution changing its color from colorless to purple, you immediately know that the solution is reached close to the equivalence point. Another type of dye you can use is called methyl red. Okay, this dye only changes color between pH level between 4.2 to 6.0. Okay, only at this pH range, this dye will respond. It will change the color to orange. So this is how you can use the metal red to detect the equivalence point. During the titration, if the solution slowly turns orange, you know that you have just passed the equivalence point. You know that the system pH value is around 6.0 and dropping down to 4.2. So if you're working with a system where equivalence point with pH around 8.3 to 10, you want to use the phenolphthalein. What happens if you use methyl red? The dye will turn its color to orange even before the system reaches the equivalence point. So this tells you nothing whether your system has reached the equivalence point or not. Okay, so um, so as you can see here, if the equivalence point has a pH value around this range, you want to use a phenolphthalein. You don't want to use a methyl red because the methyl red changes color responds to this level of pH, and even before it reaches the equivalence point, it will already change its color to orange. Then you can't really tell whether the equivalence point has reached or not. Okay, so in order to measure the pH value over the course of titration, you can use either pH meter, a device, or an indicator, but indicator of right choice. Okay, so on the Macmillan Achieve, there are various exercises about the um, the pH indicators, and after finishing that homework exercise, you will have slightly better idea of how this works. Titration of polyprotic acid, we're going to skip this. Okay, we're going to skip this. Solubility. Okay, I was going to finish up to solubility, but I guess this is it for the exam 2 material. I don't want to go over time. So this is end of exam 2 material. The exam 2 will cover up to the indicators part. Okay, so anything beyond this within this chapter is not going to be on the exam. Does anybody else have questions about exams or anything else?
I have a question regarding the homework.
Yeah.
So you told us to go up to what number?
I don't know the number, but just finish up to the indicator part in the homework.
Okay. And are the rest of the questions going to be taken off, or are we going to move them for
No,
the week after?
you will eventually have to finish it. So that's why I'm postponing the
Mm.
deadline.
Okay.
Yeah, but
All right.
in order to be well prepped for the exam, you want to do the homework. You know what I mean?
Right, as a practice.
Yeah, as a practice.
All
Okay,
right.
but the
Thank you.
due date will be postponed to
Okay.
very later. Okay, yeah.
Thank you.
Dr. Lee, I have a question about the exam.
Yeah,
Will you also be sending out a study guide over the spring break?
yeah. So I will send out this study guide on Monday.
Okay, this
Yeah,
coming Monday?
yeah. Well, Monday, March 14th, because I have to create an exam first and then create the study guide. So it's gonna take a few days for me. So, yeah, Monday.
And then the homework, will it not be due this weekend or this Sunday?
No, so I have to postpone the homework deadline.
Okay.
Okay, but again, you want to do the homework up to the indicator part because that allows you to the practice be prepped for the exam. Okay, so make sure you do your homework. Okay,
Okay, yeah, I
even though
already
it's
did
not
it.
due. Yeah,
I already did it up to the indicator part, so I could just leave it as is for now then.
yeah. The due date will be postponed.
Cool, thank you.
Uh-huh.
Dr. Lee, I have a question.
Uh-huh.
Is it possible to upload the notes up until this point so we
Yeah,
can study right
yeah,
now?
yeah. I will. Okay,
Okay, thank you so much.
I will.
And just to clarify, we're doing chapters 16 and 17 on the exam, right? Or are we also adding chapter 15?
Only chapter 16 and 17 for exam 2. Final exam is comprehensive. So final exam will consist chapter 14, 15, 16, 17, 19, 20, 24, 20. Yep. So but for the exam 2, it's only going to cover chapter 16 and chapter 17 up to the indicator part. Okay?
Got it. Thank you.
Okay.
Professor,
Professor,
sorry, sorry, go ahead.
oh no, you go. It's fine.
Okay, so I'm just like still a little confused. So you said do the homework up to the indicator part, but like, are we gonna get points taken off for the rest, or do you want us to eventually finish the whole thing when it's due?
You will have to finish the everything eventually, but I wasn't able to finish the lecture, right? So then I can't make it due this week. That's not fair. So I will extend the deadline for you guys. You know what I mean? But try to finish the homework up to the indicator part so that you are prepared for the exam. Does that make
Okay,
sense?
and then yes, and then
Yeah.
after the
Yeah.
exam, that's when we would finish the rest, correct?
Yeah, after the exam, I will finish the lecture for the rest of this chapter, and then you will eventually have to finish the homework for the rest of this chapter.
Okay, that makes sense. Thank
Yeah.
you.
Yeah. So make sure you you know, after the exam, sometimes, you know, some people don't even bother to look at the later chapter for 17, but you do actually have to study because some of that material might be on the final exam, right?
Dr. Lee, quick question.
Uh-huh.
For exam 2, is there a set date yet, or?
Yeah, March 22nd.
Okay, thank you.
March 22nd, 1 p.m. to 2:15 p.m. Okay? Is just going to be same as exam 1. Lockdown browser will be used. Okay?
Professor,
Uh-huh.
for the extra credit, you want us to choose any of the sample questions for chapter 16 and 17, right?
No, you have to do everything, but once. Okay, you don't have
Okay,
to, yeah, you don't have to show me you solved it 3 times. You just have to show me that you solved it once. Okay? But
all right.
yeah, but to prepare for the exam, I want you guys to solve it as much as you can.
Okay.
As many times as you can. Okay? But yeah, I will post the detail on Web Campus so you will have a better idea.
Yeah, and
Hmm.
also, I don't know if you remember, but last exam, you told us that since the class didn't do very well, you would round for the midterm.
Yeah, midterm grade will be curved.
Okay, and that has nothing to do with the extra credit points.
Um, the extra credit point is for the exam too. Yeah, but
Yeah, but
then
it doesn't go.
yeah, the the midterm grade will be curved.
Okay,
Hmm.
all right, thank you.
Yeah, it's just so that I